All right, for part C, the average runtime and the best case runtime of a single call to choose random pivot. So what is meant by average runtime? Average runtime comes into play when you have a method that involves something random. In our case, the randomness is with the choice of our pivot. It's somewhere between 0 and 1. It could be 0.1, it could be 0.99999. But on average, the expectation, the expected value of the pivot is going to be around the median, which is 0.5. So let's consider the average runtime as having a pivot be around the median, okay? So with that in mind, what is going to be the runtime of this choose random pivot? Well, we're gonna have this for loop, which is going to take theta of n regardless, right? We have to literally traverse the entire linked list to update its size. And then we get the index, which is going to represent the location of our pivot. And in the case of the average runtime, right, this index is going to fall in the median, right? So it's going to be size divided by 2 approximately. And so we're going to go through this n over 2 times, which is really just equal to theta of n. And so adding these two together, we get theta of n for average runtime. Okay, so now what about the best case runtime? The best case runtime is when we can minimize the number of iterations that we need to go through the linked list in order to find the actual pivot at the index location. But if you think about it, we have this for loop beforehand. This for loop doesn't care what our pivot is, right? We haven't even gotten our pivot by this point. So we're having to go through this for loop, which is linear traversal. And so even if in our best case, our index is, let's say, 0, right? So it's the very first element. We don't have to go through the while loop more than once. Or we don't even have to go through the while loop at all. We can just return the first item. Even in this best case, our runtime is dominated by this for loop. And so we can only do theta of n best case runtime.